Here we have a v versus t graph, and we don't have a short interval between t0 and tf. We have a longer interval, and we want to determine for this particular velocity profile how far or what the change in position of our object is between time t0 and tf. We could begin by dividing the interval into two subintervals. Not a very straight line, but you know what I mean. Now, between this point and this point, if we drew a straight line here, the graph doesn't really deviate all that much from this straight line between here and here, but still there's a significant deviation. Similarly, if we were to draw a straight line from here to here, the graph would, for the most part, be somewhat above that straight line, but it would be fairly close. So if we were to use two trapezoids to approximate this graph, one between this point and one between this point and this point, the sum of the areas of those two trapezoids would give us a good approximation, but not a great one, a good approximation at least, of the change in position of the object whose velocity function is being represented by this curve. Of course, there's no reason to stop with just one subdivision. We could, not doing very well with vertical here, we could subdivide again. Now we see that on this interval we're pretty close to a straight line. Now this interval, it's humped up a little over the straight line, and on this one we're pretty close to a straight line. No reason to stop there. Matter of fact, we can just divide this graph into as many intervals as we want. And having done this, each interval is approximated by a trapezoid, and the straight line at the top of that trapezoid stays very close to the curve. Not only that, but the slope of the segment at the top of each trapezoid is pretty much the same as the slope of a tangent line at any point of this curve. So that the velocity for any time within a given interval is pretty close to the slope we get from the trapezoid. Corresponding to that interval. In other words, this trapezoid right here has an area that's very close to the change in position of the object between this time and this time, and the velocity of the object doesn't change much between these two times and is always pretty close to the slope of the approximating trapezoid. Now, I'm not going to go into the calculus proof. You should be aware of how that works out from your calculus course, and you might want to review some of the theoretical underpinnings. But if we take the limiting value as our time subintervals approach zero, we get the integral of this velocity function from t0 to tf, and that is going to be representative of the area here, and the area is going to represent the change in position. So we could say the area is the integral from t0 to tf v of t dt, and that's the change in position between these two clock times. And also the slope at clock time t is the value of dv dt, the derivative of the velocity function at that clock time, and that's equal to the acceleration at that clock time.